Welcome to this 2019 Distinguished Speaker event from Geography. And it is my pleasure to introduce this year's distinguished speaker, Dr. Gavin Schmidt, who joins us from New York. And so this event is something that we try to organize annually. And the intent is to bring an influential scholar to the Department of Geography to interact with faculty, grad students, and postdoctoral fellows, and yeah, sort of engage intellectually. So Gavin, do you want to come here for a moment? So it is my pleasure to introduce Dr. Gavin Schmidt.
Well, I was checking my Twitter feed.
Who's busy with his phone. So he's the director of the NASA Goddard Institute for Space Studies in New York, and he is interested in past, contemporary, and future climate. Gavin was an author of the book Climate Change, Picturing the Science, that was published in 2009. And in 2011, he was the inaugural recipient of the American Geophysical Union Climate Communication Prize. So he is a fellow of the American Geophysical Union and also of the American Society, the American Association for the Advancement of Science. And Gavin was already here in Vancouver when in 2014 he gave a TED Talk that was viewed over 1 million times. And just yesterday, Gavin was named as one of the 100 top most influential people in climate policy. So it is an honor to have you here. And those who are interested in following Gavin on on Twitter.
I tweet a lot, but not that much.
His Twitter handle is Climate of Gavin. So the floor is yours. Thank you.
Thank you very much. Thank you. I like the way that these distinguished speaker sessions start off, because it never actually says what you're distinguished by. So you can judge how I am going to distinguish myself. Okay, I have to change this over. Oh. Okay. Okay. I'm going to talk a little bit about the role of complex modeling in climate science. People often don't like complex modeling. They think it's too complicated. Models should be as simple as possible, and these are not simple at all, and therefore they can't be the right tools for the job. And so I'm going to try and tease out a little bit about what's really going on there. Why do we build these models? Why do we think that they have any credibility? And what that teaches us about the real Earth system. So what are models for? Right? This is a very general statement. What are models for? Right? So basically, we use models to quantify our theories. Right? It's all very well saying this is affected by that and this and all these things. Once it gets beyond one or two variables, you have to be able to quantify it in a more rigorous manner. So models are there to quantify our ideas about how the climate system works. We use them to understand observed phenomena. We use them to try and understand why an El Nino event happens, what's happening when there's a frontal system that moves through. Why do we have frontal systems at all? We're trying to explain these observed phenomena. We use models to explore what-ifs, scenarios, ridiculous ideas for how you think something might have worked in the past or in the future. You can't do that with observations, so you have to use models. We use models to attribute causes. Something happens, why did that happen? Right? Take away all the things that might have caused it, see what you're left with. How do you attribute those changes? And of course, that involves a lot of what-if scenarios, and so again, you need to have a model to be doing that. And of course, we need to be making predictions. Right? If your model has no predictive capability or no skill in predictions, then you really have to ask yourself what it is that you're doing. Now, predictions can be of many different things. You can make predictions of something that's actually going to happen in the future, like a weather forecast. You can make predictions about things that might have changed in the past that we might not have detected in the observations, or something we could go and look for in the observations. And we can make predictions for things that happened, a long time ago that we might be able to find observational evidence for later on. But predictions are key. So the question I really want to have you all ponder, and that I'm going to try and answer by the end of this talk, is, do we have any right to expect that imperfect, incomplete models of complex phenomena like the Earth system, should they provide skillful predictions? Do we have any right to expect that they are skillful and useful? That's the question. So, here is a complex simulation of the Earth system. What you're looking at here are aerosols, small particles in the atmosphere. The orange particles, that's dust that's coming off the Sahara. The white wispy stuff, that's sulfate pollution coming from industrial burning of high sulfur coal. The blue that you can see in the ocean, that's sea salt being whipped up by the winds in those storms. The red dots are fires that are producing carbonaceous aerosols, black carbon, secondary organics, and organic carbon aerosols. And you can see that the whole system is wrapped up together. All of these things are being moved around by the weather systems, by the fronts. You can see some tropical cyclones forming in the Pacific and moving across to Asia. They're bright white, bright blue because of the amount of sea salt that they put into the atmosphere. All of these things are emergent properties. You're not looking at individual subroutines, you're not looking at individual processes, you're looking at the agglomeration of all of the different pieces that come together to make the wave patterns that you see going around Antarctica, that come together to make the circulation patterns that you can see in the mid-latitudes and in the tropics. We're most interested in those emergent properties. We're not, what we hope is that by understanding the small-scale effects and how they interact, that we can predict these large-scale properties as we see them in the real world. And we see patterns like this in the satellite data, in observations, all the time. And so what you're seeing is something that has a lot of fidelity to the real world. And of course, that's a volcano that just went off just near Madagascar. And that's sulfur dioxide that's slowly dissipating. All of those things are affected by the weather and by the climate, but because they interact with radiation, they are also affecting the climate and the weather. And so there's this massive feedback loop that involves all of the components interacting with all of the other components. And it's not reducible. It's not reducible to a global mean simple energy balance calculation, though obviously you can do that. The complexities that you're seeing here, it's fundamental to the system that you're looking at. So what do I mean by skill, right? So there are kind of popular, or kind of common understandings of the word, but in this sense, I'm talking about something very specific. A model is skillful if it gives you better results than you would have had without it, right? That isn't saying that it's perfect. It isn't saying that it's without error or that it's without uncertainty, but it's better than what you would have had without it. So weather forecasts are skillful. You make better weather forecasts using a model than you do by assuming that the weather is going to be the same today as it was yesterday, right? You have, you could do other ways of weather forecasting, but in fact, none of them are as good as weather forecasting using complex models. They are obviously and predictably skillful. Can we do that for different classes of models? Can we do that for climate models as well? And so that's really the test. So a model result is skillful if it gives a better prediction than you would have had otherwise. So what's wrong with models, right? Well, this is a long list, and I'll give you just a short summary. There are bugs in the code. There are approximations in the parameterizations of the things that you can't a priori model for at the right scales. There are inaccurate forcings, whether it's the amount of solar radiation 100 years ago or the amount of aerosols in the pre-industrial climate or even today. There are errors in discretization. The fact that you have to chop the model grid into finite pieces gives you errors in topography, gives you errors in frontal structures. In models, there are a lot of common but perhaps erroneous assumptions. None of the models in the CMIP archive are eddy permitting or even eddy resolving in the ocean. So all of those models have a particular bias towards smoother ocean circulation than we see in the real world. Right? So that's a common assumption that is unfortunate, but it's obviously erroneous. And of course, because these are chaotic systems, we have to worry about things like the size of the ensemble and the length of the spin-up and climate drift, and all of these things that we would like to do a much better job on, but we, for lack of computational power and time, we don't do as good a job as we could. And of course, the parameterizations that we are building and that form the basis of these codes maybe overfits to observational data that might be limited in some way, right? So, you know, you're trying to calculate the amount of activation of aerosol or cloud particles as a function of humidity. Maybe the data that we have is not sufficient for us to actually find the true function of what controls that. So there's lots and lots of reasons why we know and we suspect that models are wrong and imperfect. Yet the interesting thing is that model skill is improving, right? This is a totally ad hoc metric that these guys, Thomas Reichler and Kim, put together. And this is different generations of models. So CMIP 1 was back in the 90s, CMIP 2 was kind of in the late 90s, CMIP 3 was in the early 2000s, there's a CMIP 5 that would come after this, and there's a CMIP 6 which we're just starting now. As you move towards the left-hand side, that's better in some kind of ad hoc way. And as you can see, the population of models is moving towards the left-hand side, and so in some sense, they're getting better. Now, there's a couple of interesting things about that. The black dots is the average of all of the models. Now, the average of all of the models turns out to be a better predictor of the real world than the best model that you can find. And that's true in almost every single variable. And if you think about it, that's actually quite surprising, right? Why should all of these models kind of cancel out and give you a better answer by averaging them all together than just picking the one that's the best model? But it turns out that is significantly the case. And that's a puzzle, anyway. But it's clear, if you look at these models, and this is our latest and greatest model that's going to be in the CMIP 6 archive, that there are clear biases in key issues that have always been problems for models. So low clouds, particularly in the marine stratus region, so kind of just off the west coast of the US and South America and Namibia, that amount of cloud, we're not getting the right amount of cloud in those low marine stratospherics. It's a hard problem, and even our bestest model so far doesn't do a very good job at capturing that. And I could pick precipitation, I could pick high clouds, I get any variable where there's a lot of intermodal heterogeneity. You will find that there are clear errors that persist in generation after generation of models. So here a little bit of philosophy for you. All models are wrong, right? You don't need to think very deeply about that. I've given you a dozen reasons why these models in particular are wrong, but it's actually true of all models. Quantum physics is wrong, special relativity is wrong, general relativity is wrong, Newton's laws are wrong, but they're still very, very useful in the domain in which they are valid. So, to what extent is this true for climate models? So, all models are wrong, yes, and it's just very easy to see that with complex simulations. Yet, so here's a hindcast of the 20th century in the CMIP 5 runs that we did. This is the model and these observations. They've been slightly smoothed to remove some of the large weather excursions. So, but you see the blue and the yellow, that's the weather, and it's uncorrelated from the models to the observations because you can't predict weather, 50 years ahead of time. And so we're not really looking at the weather. We're not looking at the ups and downs. We're looking at the pattern that's starting to emerge here in the 1990s. And now, as we get to the 2000s, we start to see a much clearer pattern that is actually the same to a large extent in the observations as it is in the model. And you go, how is it that a model that's demonstrably wrong produces in hindcast the patterns that we actually see in the observations? We can do this attribution thing. So I can explain why those models get the pattern that they do. And the kinds of explanations that we look at are natural variations, changes in the orbit, changes in the sun, changes in volcanoes. Those are all natural things that have been happening over the 20th century. If you put them all together, do they produce the global mean temperature changes that we can observe? What do we think? Come on. No, of course they don't. And it turns out that you're about 5 sigma off in terms of the internal variability from what you see. So that's a detection of a change. Now we can look at all the things that we've had influences on. So land use, chopping down forests, aerosols, ozone pollution. We can look at all those things. And of course, greenhouse gases, the increases in carbon dioxide, methane, nitrous oxide, and CFCs. And they would have warmed the climate more than we've actually seen had they only been operating on their own. You put together all of the human factors, and what you end up with is a good estimate of the trend. And of course, if you include the natural factors, which have obviously been part of the problem, part of the situation as well, you end up with an extremely good match to what has actually happened at the global mean. How do we do that if the models are all wrong? Now, this has been said by other people, and so I'll just quote them. If we had observations of the future, we would obviously trust them more than models. But unfortunately, observations of the future are not available at this time. So, prediction. What can we say that's skillful about the future? Now, you've all seen some pictures like this. This is the 21st century projections under various RCPs. The one that says aggressive mitigation, that would be consistent with the targets that people aspire to in the Paris Accords. The business as usual is basically burn it all. And so that's what you would get if we continue to increase emissions at the rate that we are continuing to increase emissions. And then serious mitigation, this is RCP 4.5 for people that care about that. But it's something in the middle that you could think about this as totally impossible, very, very scary, and conceivable, right? And the changes that you're seeing there are massive, right? So even under the serious mitigation changes, you're looking at ice-free Arctics in the summertime. You're looking at 4 or 5 degrees annual mean temperature change over a large part of the continents. And there's a few places where it's still relatively stable, particularly in the Southern Ocean and in the North Atlantic, where the ocean circulation is conspiring to mitigate the changes that you're seeing. But if we were to end up here in this the RCP 8.5 realm, I mean, this is a totally different planet, right? So for contrast, the Ice Age, right, 20,000 years ago, about 4 to 5 degrees cooler Celsius than the pre-industrial. And this is 4 to 5 degrees warmer than the pre-industrial. So this is one Ice Age unit in the other direction. So if you think about the Ice Age, totally different ecosystems, totally different sea level. It's not totally symmetrical, but this would be as well a very, very different planet. Now, how do we know that these models are any good? How do we know that these predictions are useful? Now, we have some problems, right? So you might think that well, we should just look to see whether the models get something right, and then we should trust that model more. Right? We should weight the models towards the models that get something right that we care about. The problem with that is that when you look at different things, whether it's the mean climatology or the seasonal cycle or the interannual variability, it turns out that the ranking against one measure of skill is totally uncorrelated to the ranking against another measure of skill, which is uncorrelated to a third measure of skill. And so the notion that we can just say which model is the best is very ambiguous. But it gets worse. The bigger problem is that the skill is not correlated to the prediction, right? So you can find, well, however you want to do it, you find the model that has the top 10 models that have your particular metric in mind, and you say, well, I'm just going to take those 10 models, and I'm going to project forward just those 10 models out of the whole ensemble. And what happens is that you just get exactly the same answer as if you'd just taken the whole ensemble. And you say, well, what was the point? The point is, why does that happen? It turns out, for instance, even as the skill decreases, right? So as you go down, that's better, that's higher skill. And this is the climate sensitivity, but you could pick any particular metric for the future. What you find is that all the models, that there's no preferred measure of sensitivity that is just the ones that are associated with any particular level of skill, right? So the spread in the models in CMIP2 and in CMIP3 and in CMIP5 is pretty much unchanged, even though the skill of the models is increasing with every generation. You might notice there's one green dot here, which you think, oh, well, that's the best model ever. And that was from CMIP2 like 20 years ago. But it turns out that they fed in the right answer through a flux correction methodology, so it doesn't really count. So the fact that skill doesn't correlate to projections is a really important issue. So what people do instead is they do model democracy. So we just average all the models together and we say that that's our best estimate. And that's a terrible idea. It's terrible. It's obviously the worst scheme that you could ever have thought of, except for all the others. And it turns out that it's almost impossible. In fact, nobody has done it yet, so it may actually be impossible. It is impossible, perhaps, to come up with a weighting scheme that actually significantly beats model democracy time after time after time. It's very confusing because model democracy is like we're averaging in, like, here's the good models and here's the bad models, and we're averaging them all together, and we're actually getting something that's better than any of them. It goes against what it is you want. I want to make my model the best model. I don't want it to be like contaminated by all those other inferior models, and yet when it does, I get better results. Very puzzling. So what you should be looking for are not future changes that don't correlate to a skill score or a metric that you're particularly worried about. I mean, so you want to know what's going to happen to the Indian monsoon, and you take all the models that have the best Indian monsoon right now, and it turns out that the change in the monsoon is uncorrelated to the skill of the monsoon prediction for today. And you go, so it looks like this. That's no good. You want to have something instead where the skill and the future change have some relationship, right? So in a situation like that, you might say, oh, well, the one with the best skill has a future change that's, kind of in the middle of that graph. But it turns out that there's only been about half a dozen things that people have looked at that look anything like this. And people have looked. I mean, people have used machine learning to look at, thousands and tens of thousands of correlations of variables and skill and metrics, and we still haven't found more than about half a dozen things like this, which is problematic. So one of the things that you can do, of course, is you use out-of-sample tests to evaluate how well your models are doing. And so there are lots of different out-of-sample tests. So Paleo Climate is a great one. Nobody uses Paleo Climate change to calibrate or change their big system models, with a couple of exceptions that we could go into. But generally speaking, the CMIP models are not trained on Paleo Climate. And of course, you can make a prediction for the future, which is obviously out of sample, right? Because you're trying to predict something that hasn't actually occurred. But I work for NASA, and so some of the things that we can do are a little bit more interesting. So we can use RGCM to look at climate on other solar system terrestrial planets. So, we run our model for, Venus 3 billion years ago, which actually turned out to be a pretty nice place. Mars, when it had water, we're simulating the climate of Mars then. And of course, exoplanets. We're spotting exoplanets at a massive rate. These days, exoplanets are planets around other star systems. We've now identified more than 5,000 such planets. With that information, we often get things like how close in the orbit is, how big the planet might be, what kind of star is it around that affects the climate. And possibly with the launch of the James Webb Space Telescope, we'll be able to get direct imaging through atmospheres of some of these planets in the relatively near kind of galaxy part of the galaxy. And if we can predict what we might be able to see there, right, if we could predict, the climate of an exoplanet around Proxima Centauri, which is not that far away, that would be, I think, an interesting validation of our approach. But all is not lost, right? So, I mean, we can go back to the Paleo Climate. We have a lot of data from Paleo Climate, and you can get interesting relationships that you can find in these models are actually quite robust, right? So this is the temperature difference over the oceans versus the temperature difference over land in the tropics across a whole different range of scenarios, right? So the red ones up there, those are future warming scenarios. So what it says is that the models expect that the warming over land is going to be slightly larger than the warming over the ocean, right? The amount of warming depends on the sensitivity of the model, so you're seeing a spread there, but they're all kind of on a line, which is interesting. You can look at the past ice age simulations, those are the blue dots, with those same models, and you can see, oh, well, actually it's on the same line, right? So going forward into a warming climate or going backwards into a cooling climate, the relationship between the land and the ocean temperature change is actually pretty robust. And the joy about the paleoclimate is that we can go back and we can actually interrogate the proxies and ask, well, what was it? What was it in the past? And that's the blue dot there is actually all paleoclimate data that also falls on this same line. So if you were to ask me, do I think that this is a robust projection, that the oceans will warm slightly less than the land in a future prediction, I would say yes, I think that is a robust projection, and I don't think that there are many assumptions that go into it that would undermine that. Now, we've been doing modeling for a while, right? So how have our future predictions been working out, right? So 1981, we didn't have GCMs. This is a relatively simple energy balance model, and that underpredicted the warming that we subsequently saw. In 1984, this was the first GCM to do a transient simulation of what was going to happen. And again, you can see there's a slight overestimate of the warming, but that actually turns out to be because they expected more CFCs and more methane to go into the atmosphere than actually occurred. CMIP 3. Again, the gray bar is the spread of the models in this exercise, and this was done with observed data to 2000 and then forecasts from 2000 onwards. So we've had almost 20 years of true forecasts in these models, and we're pretty much directly on target, which is interesting. We did it again in CMIP 5. This was done 5 years later, and like I said, we're just about to start CMIP 6 now. Again, the gray bar is the ensemble of the models. The observations are the colored lines, and we're just a little bit shy of the model mean. And I think that that's one of the reasons for that is the forcings that we used in that particular experiment were slightly overestimated. But again, we're still pretty much on target. Let me just talk very briefly about the Hansen et al. 1988 paper. So this was a paper that was published in 1988. It was the first transient simulation. It had multiple scenarios, a high forcing scenario, a middle scenario, and a low scenario where things kind of stopped changing after about the year 2000. This is the picture from the graph, and so this is that data. But then if you actually think about the scenario that was closest to what actually happened, which is the scenario B, which is the middle scenario, it turns out that it overestimated what the forcings were going to be. You can correct for that in the trend. And, oh, no, again, I guess. Let me do that again. And it turns out that that once you do that, the model actually turned out to be quite quite skillful. And given that everybody else back in the 1980s was saying climate change had not been detected, we weren't going to see any changes in the near term. That would be the null hypothesis, the persistence the hypothesis. What we saw with these models runs was clearly that the models were skillful. They were better than the naive hypotheses that people were putting out instead. One of the key metrics for demonstrating that these models are changing for the right reason is this notion of ocean heat content, right? So the models are suggesting that climate is changing because there's an energy imbalance at the top of the atmosphere. There should be more energy coming in than is going out because of the increases in greenhouse gases. When that happens, there's more energy coming into the system. Where is that energy going? Because of the large heat capacity, it has to be going into the ocean. And so way back in 1988, Jim Hansen said, we stress the importance of measuring the rate of heat storage in the ocean. The best opportunity for improvement in our understanding of climate sensitivity is monitoring internal ocean temperatures. Now, this was in 1988. It took more than a decade for the first reasonable estimates of this quantity to be published, and it took another decade after that for the first correct estimates of this quantity to be published. And when you do that, what you find is that these models that were run before that data came in end up matching the data and the rate of change of ocean heat content to a pretty strong degree. And when you go back and you look, this is the comparison to the 2012 estimates of those things, and these are the models in the blue. You can see that the match to the reconstruction of ocean heat content is actually a really good match to what the models suggested it should have been. And so this is a prediction of something that happened in the past, but when the prediction was made, we didn't know what had happened in the past. And so it's a true out-of-sample prediction. When things happen very quickly, like Mount Pinatubo was a great example, went off, erupted in June 15th, 1991, and within 3 months, our group, this is obviously before my time, but had run the experiment and submitted this for publication to predict what would happen over the next 2 to 3 years because of the impact of Mount Pinatubo. Right. So this was the prediction that they made. The changes were expected to be on the order of 0.5 degrees cooling. It didn't turn out to be quite that large because the estimate of sulfate forcing was a little bit too large in these experiments. But in fact, it was about half that, a cooling of about 0.3 to 0.4 degrees Celsius, and then there was a big El Nino in the middle, which obviously wasn't predicted in those models. So there was so if you can see, it cools and then it gets warmer again and then it cools again. But the length of the perturbation and the first order magnitude, 0th order magnitude, is still pretty good. And when you do that again now with better estimates of what the actual sulfate forcing was, you can match the observations that you actually saw really quite well. And it's not just the temperature, right? The volcano changed the structure of temperature gradients in the stratosphere and troposphere. It changed the winds. It changed the precipitation. All of these things can be seen to have been predicted ahead of time skillfully. So when you're combining theory and experiment, right? So it turns out that each model is basically its own theory of climate, right? So there isn't one theory of climate that each model tries to get exactly. Each model, because of the different parameterizations, the different processes that are included, are basically independent theories of climate. And their skill in modeling the emergent properties need to be tested, but they are there to be tested. When we look at robustness of results, we're not talking about getting the same answer with the same model and just running it over and over again, right? We're talking about, in a similar way to lab experiments, can this be reproduced in another lab in independent situations? So, to the extent that another climate model is independent of this climate model, does it produce a robust result? That's a very important aspect of assessing robustness. And reproducibility obviously a key issue with models. You're much more interested in independent replication than you are by rerunning the same code, right? You don't want to redo the same bugs that are in one particular model. You don't redo the same approximations. You want to demonstrate that a result is true, or that a result is not true, that a result is reproducible, with a different set of assumptions and different people doing those runs. So here another bit of philosophy. People have often said that complex simulation is a third pillar of science. Like, so you've got theory and you have experiment, and then you have computation would be something else. But in my view, it's just a little bit of both. The models themselves are an encapsulation of your theory, but you have to treat them as though they're lab experiments. And that makes working with them a little bit complex, but it doesn't make them a totally new way of doing science. So what do we do when we have model observation discrepancies, right? So these can happen for a number of reasons, right? So the models are wrong, and so it doesn't look like the real world because the models just don't include something, or they get something wrong, right? So for instance, we have a double ITCZ problem in these models where instead of having one rain band across the equator that moves up and down smoothly, we end up with two bands that straddle the equator. Now, we know that that's wrong. That's not actually what happens in the real world, and yet models, generation after generation, have this tendency to produce a double ITCZ, right? So that is, the models are wrong. They're missing something. Observational data are imperfect, right? Some of you might remember the whole satellite data show that the planet is cooling debate in the 1990s. And it turns out that the planet wasn't really cooling. It was that the calibration of the satellite data was incorrect. So the models were actually correct. And sometimes we have discrepancies because we're not comparing like with like, right? So this is a picture of low clouds as seen in the ISCIP data set. So this is a satellite data set of clouds. And when you look at the low clouds in the models and you plot it against that, they don't look anything like each other. You go, oh my God, you're doing such a terrible job with low clouds. But then you think about it for a second. You say, well, what does a satellite see to see a low cloud? It can only see a low cloud if there isn't a high cloud. And so when you're comparing a low cloud that's been observed from a satellite, you have to be looking as if you were a satellite. So if there's a high cloud in your way, then you don't see that low cloud. And it turns out that you have to do a lot of work to build emulators of particular observing systems, particularly satellites, in order to get comparisons that are worthwhile doing. So you've got those three things, right? The comparison might be wrong, the models might be wrong, and the data might be wrong. And all of those three things happen all the time. And you can't assume that just because there is a model data discrepancy, that it must be the model's fault. Here's a complex figure, and it's a complex mechanism, right? So how do changes in the sun affect the climate? And it turns out that they can affect the climate through many, many different ways. The total amount of energy that comes in, the UV portion of that energy, solar energetic particles affect upper atmospheric chemistry. The temperature changes in the UV affect the ozone. It can affect all sorts of modes of variability. There are speculative ideas about galactic cosmic rays causing ionization, which cause clouds. Turns out that that's a very, very small term. But there's a lot of complex things going on. And so how am I to understand the changes in the atmosphere because of solar forcing if I don't include all of that complexity? I have to capture that complexity in order to match what's going on. So, this is a very, well, actually it's probably way too much detail, but anyway. The observations, the raw data from the observations, and this is in different temperatures going up through the stratosphere. How big is the solar cycle? Right? So how big is the solar cycle in the lower stratosphere, mid-stratosphere, and then upper stratosphere? And there's some simulations there. So the reds are simulations and the blues are simulations. Now the blues and the reds should be the same thing because they're the component of the variability that's associated with the solar cycle in a bunch of different runs. And so you think, well, unless there's some really difficult nonlinearity, you should think that if I do it one way when there's only solar forcing happening, or if I do it another way where everything is going on, I just extract out the solar part, I should get the same answer, and I don't. And you go, that's interesting. But when you take out the biasing of changes because of volcanoes, which happen to have an 11-year cycle as well, you end up with a situation where the models all line up. So this is the blue and the pink, and the blue and the pink and the black, or the blue, pink, and the gray. And it turns out they all line up if you do the analyses properly. And so by adding complexity, so this is, we're adding in interactive chemistry, we're adding in interactive ozone, aerosols, and high stratospheric processes, we can actually get a much, much better match to the observations by adding complexity. Okay, so here's where I rag on Richard Feynman, who was very brilliant in many ways, flawed in many ways, but off-quoted. And he's often quoted for this particular quote. It doesn't matter how beautiful your theory is, it doesn't matter how smart you are, if it doesn't agree with experiment, it's wrong, right? So model falsification there, if your model doesn't match up with some observation, throw it out, start again. Except this is not how science works. It's not even how his science worked, right? So this is just a totally wrong statement. Some of you might remember the discovery of faster-than-light neutrinos a couple of years ago. And as I'm sure you're all aware, we have subsequently thrown out special relativity because of that. No? Oh no, the observations weren't perfect. This is the problem, right? There are many, many reasons for a discrepancy, and this kind of simplistic view, which I don't think he actually believed, but this kind of simplistic view does not reflect the complexity of the tests that we're actually doing. Discrepancies in comparisons can have multiple causes. And so technically, this is something called Duhem-Quine underdeterminancy, which means that if you have an error, there could be multiple reasons why you have an error. And when it comes to complex climate modeling, this is almost always the relevant thing to be thinking about. Right, one more thing. So here's another slight digression. So that attribution animation I showed you, right, that came from Bloomberg News. What was the data compression involved in making that figure, right? So I'll tell you that there were 6,502 data points in that figure, right? How much data did I need to crunch in order to produce the 6,502 data points that I actually ended up showing? Do you want to give me a order of magnitude ratio? 10 times as much? 100 times as much? I don't know, 10 to the something? 10,000. Anybody else? Higher. Yes, so I was showing the global mean of a simulation. Higher. Okay, so data compression, I estimate, is about 10 to the 9. So it's about 1 billion to 1. Right? So I needed to crunch 1 billion bytes to produce 1 byte of data that you saw there. So the total amount of data that I was crunching was large, which is a small fraction of the amount of calculations that I did to get there, right? Not that I did, that the computer did. So it's about 1 billion to 1. How many other stories and results could I have pulled out of that same data set that I didn't show you? Right? Okay, there are all these billions of data sets that, they're all connected in some way, so it's not 1 billion stories. But, maybe it's tens of thousands of interesting results. Why did I only show you that one? I showed you that one because it's very easy to calculate, because I'm calculating the one variable, I'm calculating the global mean, and as a function of time. It's very straightforward, and our archives are built to make that very, very easy to calculate. If I want to calculate any of those other tens of thousands of stories, it becomes much more complicated. And we are producing so much data, right? So CMIP3 produced about 5 petabytes of data. CMIP6 will be about an order of magnitude larger. And sure, your USB sticks are doing great guns in terms of increasing the amount of storage that you can download, but you're not downloading 5 petabytes of data onto your hard disk. So the data science challenge is really a very hard one. I was looking at annual data. I have hourly data, right? Am I looking at hourly data? I'm not. If I really want to make those like-with-like comparisons, I actually have to do a lot of work with those emulators and with that sampling and the issues. Am I doing that? No, because that's a lot of work too. Data mining in those archives, unless you're going to do something very, very straightforward and simple, is almost impossible. I'll give you an example. And these examples arise from the fact that these data archives, they're not optimally designed for the best kinds of diagnostics. So let me throw out the idea there that if you can have a diagnostic that tells you about something that's a directly observed process that is directly associated with a very specific line of code or a very specific algorithm, a subroutine, then that's going to be the most useful thing to be looking at. Turns out that that's almost impossible. I'll give you an example. So if I want to know how storms in the model are doing compared to the real world, right, what would I need to do? Well, I need to know first what storms in the real world are doing, right? So let's compare models and observe storm systems in the North Atlantic. So first of all, I would find the storms. I would have to find some tracking algorithm that says, oh, here's a storm, here's moving around. And then I want to save all the different variables that are associated with that storm. And so I co-locate all the satellite observations, and I look at all the different satellite variables, the temperature and the ozone and the OLR and the incoming shortwave and the rain rate and the rain amount and the cloud amount and all the rest of it. And then I do the same thing in the model simulations. Each model has its own storm tracks. I have to find the storm tracks. I have to download all the data. It's all multivariate, and I have to select it on exactly the grid boxes around where these storms are going. And then create the synthetic satellite products using the emulators to compare these things to. Sounds pretty straightforward. Except that kind of filtering, multivariate, time and space dependent, model ensemble member, you have to do it for every model ensemble member independently, just doesn't exist, right? So this is a comparison that one of our graduate students put together. It took him 4 years to do this, when really it should have taken a day. And if an analysis that you want to do takes 4 years instead of taking a day, you're not going to do it. And so there are so many observational and process-based diagnostics that we could be looking at in these models that we aren't, that it's criminal that they're actually giving us more money to produce more data before we've actually finished analyzing the data sets that we have. It's not easy. So let me quickly conclude. Climate models do provide understanding. We have a better understanding of how the climate system works because of the work that we've done on climate models. Many of the predictions of those climate models have been demonstrated to be skillful, not just like very old models from the 1980s, but by up-to-date state-of-the-art models right now, predicting things that either in hindcasts or in paleo climates that we have subsequently found to be skillful. The discrepancies between models and observations are not always because of the models. And the amount of time I find myself, just saying to people, just hold on a little bit, when they say, oh, look, your model can't do X. And you're saying, well, hold on. What is your X? How do you define it? What is the actual measure that you're using? And, and a lot of times you do find that the data is not as clear as it should be, and the comparison is not as apt as it should be. And it takes a lot of time to get that right. The consequence of that is that many future predictions and projections of climate are robust. They aren't going to disappear with another generation of models. They aren't going to disappear once we add ocean eddies into the system. They aren't going to disappear because we've added a new aerosol component or a new ice sheet component into these models. And we're doing all of those things. We're trying to make those models better. But most of the things that people worry about and the reason why we have concern about future climate change, almost all of those things are robust, and they will stay so. But we could do much better. So the question I started with, do we have any right to expect that imperfect and incomplete models of complex phenomena should provide skillful predictions? What do we think? Fake you. No, you have no right to expect it. It makes no sense at all that they provide skillful predictions. They only provide skillful predictions because we have demonstrated that they are skillful, right? You have no right to expect them to be skillful. And when you don't, and when you assume that either something that's complex must be right because it's complex and it's better than your little energy balance model, that's a bad assumption. You have to test these things every single time, which is problematic, understood, but it's real. And yet, they work. That's Italian. Everybody know where that comes from? Galileo, so yes. And yet, they move. And yet, they work. And they do. And every time that they do so, and we match another out-of-sample prediction, whether it's the response to a lake burst 8,200 years ago, or the changes of rainfall with the LGM, or some other thing that comes up. He's running out of examples and just rambling at this point. It always astounds me, because I build these models. I know where the code sausage is buried, and no, that's a mixed metaphor, isn't it? I know where you don't bury sausages. Does anybody bury? No. We make sausages. I know how the sausages are made, but we don't bury the sausages. No burying of sausages. Okay, moving right along. That's it. Thank you very much.
Okay. Thank you for this thought-provoking presentation. So we do have viewers online. So for Q&A, we need to pass mics along. So I will be passing this mic here. So raise your hand if you want to ask a question. And also for those viewing online, if you want to ask a question, please email Nastenka, and the email address should be at the bottom of your screen. Okay, good. So please, any questions for Gavin?
Karen.
Thanks for your talk, Gavin.
Thank you.
I wanted to ask, what of the improvements that you said we should be making, what is your top priority right now for improvements in climate models?
So, I mean, we continue to work on aerosol cloud interactions, right? That's one of the most important remaining uncertainties, and the range that we have from a priori modeling is large and unconstrained by the observations. So we really need to be focusing on that. But there are a number of elements where we can't provide very good answers to very sensible questions, like how much is sea level going to rise, right? And it turns out that answering that question means you have to get a lot of things included in these models. So some parts of it are very well predicted, like so the amount of thermal expansion in the ocean in the next 100 years. Well, that's pretty well constrained, right? Depending on the scenario, of course. But how the ice sheets are going to respond, what's the dynamic contribution of ice loss in Greenland and in West Antarctica? How is that going to contribute to sea level rise? We don't have yet sufficient models that have dynamic ice sheets embedded with them, that have ocean ice interactions underneath the ice shelves and the impact that has on the grounding line. So we're still very much in the dark as to what the ice sheet contribution to sea level will be. And so that's somewhere where we're working very hard as well. I mean, everybody who has a particular speciality is going to have a list of, we need to be doing stratospheric chemistry better, we need to be doing boundary layer clouds better, and all of those things are true. But I think that the two biggest elements that have the biggest salience to people outside of the field are aerosol clouds and sea level rise, and that encompasses a bunch of different things.
Thank you for your talk. My question relates to the geoengineering that's been proposed to combat climate change.
Right.
What's the current state of the models in regards to the effects of possible geoengineering?
So there was a paper last week that came out where they were talking about geoengineering, and they didn't really do the right experiments, right? So they're turning down the sun. That's not a real thing. We can't turn down the sun. What we can do, and what people have proposed, is we can fill the stratosphere with sulfate aerosols. So we can produce the results. So when you put in sulfate aerosols associated with Mount Pinatubo, for instance, we can produce the aerosol distribution that we observed, right? So the chemistry of that, the transport of that, the impacts of that, we can model all of those things. And the answers are not unsurprising, right? So you can cool the climate, right? We can see that the Pinatubo cooled the climate. We can artificially cool the climate. But it has bad impacts on the ozone layer. So the ozone layer is depleted. You end up with deposition of increased sulfuric acid in the polar regions, which is like kind of an acid rain. There are some subtle issues that are associated with that. But the biggest problem with all of these things is not the science, right? So it's not the science of solar radiation management, right? So I mean, people are playing games. Like, well, let's turn it up only halfway. Let's assume that we can have a multi-centennial global governance pact to control this and make sure it never gets turned off once you start it. You can play all of those games within model world, but the reason why it's totally irrelevant is that is not because of the science. It's because of the geopolitical circumstances that would allow that to occur. Right, so if you think about what would be required to have a geoengineering solution, right? You need to have stability, you need to have long-sightedness, and you need to have it be, people who are losing must be compensated. Yeah, the idea that we can't, given that we can't agree to reduce emissions, the chances that we would agree to set the climate at a certain level and maintain it there for hundreds of years is insane. And so, the people who have come up with, maybe China will just decide to do geoengineering, and then there'll be nothing we can do to stop them. But the problem is a rogue effort is not geopolitically stable, right? So China decides, maybe Shanghai has flooded 3 times in the last 3 years, and the Yellow River is running dry, and Tibet is melting, and they decide, okay, well, we can't stand it anymore. We're just going to do it ourselves. And they start putting. And they could, right? I mean, it's a viable scenario for them. They could spend $20 billion a year and put sulfur dioxide into the stratosphere. What happens the first time that there's a monsoon failure in India? Doesn't have to be connected, but what happens? Now I've got 2 nuclear-armed states, one of whom is thinking that the other state is killing 100 million people in their country. What's going to happen? This is not a stable situation, right? And so the idea that you could maintain that for hundreds of years that would be required to actually reduce emissions before you could turn it off, because if you don't reduce emissions and then you just keep on going, you can't. You're making it worse and worse and worse while nothing is actually changing underneath, and at some point it stops. And when it stops, that's a disaster on a KT boundary level of disaster. So, people talk about geoengineering a lot, but the issues in geoengineering are ethical, moral, and governance related. That there's the science that you can do doesn't solve any of those problems. The front here as well.
So thank you for the talk. I was a little surprised to hear that you were in favor of analyzing first all the data that we've produced rather than producing new data, because, as you said, the development goes to more and more complexity, and I would wonder what your impression is. When are we going to plateau with the skill of the models, with the complexity? Does it not help us to add this kind of complexity to those models anymore?
Help us for what?
Well, help us answer these questions. As you said, like a lot of these old models already had like these climate change patterns, that's something that you could, if you wanted, explain in 1 or 2 equations.
Right.
So what answers do we need before we start acting on, you know, like...
Okay, so if the question is, do we know enough to start acting to reduce carbon dioxide emissions? Yes, and we knew that 20 or 30 years ago, right? So it's not because we've had more science subsequently that that answer has changed. It hasn't. The need to reduce carbon emissions was clear 30 years ago, and it's abundantly clear now. It's just that things are happening more on the ground and people are arguing less about it. Are there questions that we could be better answering with the models that we could develop in future? The answer is yes. I mean, I gave a couple of examples, right? So aerosol cloud interactions, sea level predictions, all of those things still require more development of those models. But those are questions that kind of feed into, you know, how do you adapt to what's going to happen, not whether you mitigate. So if the only question you care about is whether we mitigate, then sure, don't fund climate science anymore. Like, we know the answer. But if you want to know, you know exactly, well, not exactly, but even roughly what the sea level rise is going to be off the coast of Vancouver, you have to include a whole bunch more stuff that we're not including yet. And those are important questions too.
Thank you for the lecture, by the way.
Thank you.
So learning in class and reading multiple articles, we tend to see how models' results usually include how we need to mitigate, and then the models present results that are very similar, where in the next 10 years or 50 years, let's say carbon dioxide emissions will then reduce, and then the amount in the atmosphere will decline, and so on and so forth. Mm-hmm. So I was wondering what your thought is with future in terms of like what happens if we don't change? Would the timeline just move on, and like would the models produce the same results, but then let's say beginning 2050, would the models just produce the same results, but with changes hopefully will occur then? Or do you think there will be any different?
Let me just paraphrase what you're asking. So yeah. Does are the results that we're getting for a global mean change of 1 degree or another 2 degrees, are they robust regardless of when we might get there?
Yeah.
Yeah, so the answer is yes. So if you look at different scenarios, like high mean scenarios, low mean scenarios, and you take the periods that have the same global mean temperature change, then it really doesn't matter on the scenario. There is a difference between the transient nature of the change and the fully equilibrated changes, mainly because the Southern Ocean takes such a long time to catch up. But you know, the rate at which we get to 2 or 3 degrees warmer than now doesn't really change the patterns of change that you see.
I have a question, so it relates to the relationship between complexity and skill.
Yes.
So as we make these models more complex, we increase resolution, include additional processes, and
yes.
you lined out in which way we could go. Can we how about skill? As we build in more feedbacks, more processes into the model, can we expect skill to keep increasing? So you showed that for CMIP 1, 2, 3, the arrow went down. So what do you think about that?
So yes, I mean, so skill is improving. You know, part of it is, I mean, you could take your same model and work on it and work on it and work on it, and you will find reasons to improve the skill. You know, it could be by fixing code bugs, it could be by adding new processes, it could be by putting in new pieces of physics, and what you find is that it's not obvious that it should be the case, but as you add complexity, you end up with higher skill. And it isn't, I mean, it's not like a statistical fit where you add in more and more terms in a polynomial and you get smaller and smaller residuals. You know, these are physics-based calculations where, you put in better chemistry and you put in better photolysis rates and you put in better radiative tables and you increase the resolution, then you get better skill. It's not a linear process, right? So, if when you're modeling, and so you've got a model here that's like, your kind of base case, and then you change something, it often makes it worse. But then you change something else and it makes it better, and you change something else. But on average, you're getting better over time. And you know, yeah, I mean, we've been doing this now for 40 years. And I think that the expectation for increasing skill has come about because skill has increased over that time period. And we're still seeing areas where we know that we can do better. And so when we do better, like in the very brief example I gave you for solar forcing, when we do better by adding in more chemistry and adding in ozone feedbacks and all the rest of it, it does make a better match to the observations. And you know, we'll keep on going until that is no longer the case. But I don't know that that will come anytime soon.
Okay, good, thank you. Any other question?
So it sounds to me like you're fairly confident the models are working pretty well, yes, with caveats. Are there any places where the actual theory of climate change is broken based on what you see in the models? So is there anything in our observations that's missing, in our actual physics that's missing, that the models create or don't create, but is lacking in our actual understanding?
So there are still some big questions as to how ocean-generated turbulence impacts climate, right? So, you know, I mentioned that most of the models here that I was discussing don't include ocean eddies in any real sense. And it's possible that with more kind of self-generated noise and turbulence in ocean codes, that could change the sensitivity, for instance, of the overturning stream function to changes in water and heat in the North Atlantic. Or it might change, you know, how quickly things warm in the Southern Ocean. Or, you know, I mean, so there are interesting issues associated with that, and that's a new class of model that would include that we don't actually have, right? So it's very difficult to predict what the impacts will be, but you might think that there will be impacts. And then you've got you know, Paleo Climate results from like the last ice age. You know, you've got almost 100,000 years of last ice age where the amount of variability in the system was orders of magnitude larger than it was in the Holocene. And we think that that's associated with the existence of very large ice sheets, unstable ocean ice sheet connections that I have no reason to think would not occur in a model that had more ice and better modeling of those interactions. But it's very hard to tell because we don't actually have that model yet. You know, at that point, you might find that, for instance, ice age climates are actually chaotic, right? And interglacials are not, which would be an interesting result. But I don't know what the answer is. And so yes, so there's, you know, those two elements kind of give me a little bit of reason to pause. And then, you know, there's you know, you go back to the Eocene, right? And you ask yourself, well, why were the Eocene poles so warm compared to the tropics, right? And you look at the models, and we run models for the Eocene, and we really don't match that shallowing of the equator to pole temperature gradient. And you say, well, we know that it was warm, right? So how was it that warm without it like totally boiling off the tropics? And we still don't know. And so that means that there are potential missing elements as we get to warmer climates that we have not yet included or that we have not fully understood. And that also gives me pause. But not until we get to kind of Eocene conditions, which isn't going to happen until at least next Tuesday.
Yeah, we have a question from Christina, from one of our online viewers. How can modelers communicate the complexity, simplicity of their models to policymakers to adequately communicate uncertainties?
So we communicate uncertainties all the time. I think actually we're doing a pretty good job at communicating uncertainties. I think we're doing less of a good job at communicating the things that we're actually pretty certain about. Yeah, I mean the current US administration is far more interested in our uncertainties than they are in our results. So, you know, I mean, we have to, you know, we obviously have to be, you know, we have to have some integrity about what we're talking about, and obviously that does include, you know, the scenario uncertainty, which is large, the you know, the model, the structural uncertainty in the models, which can be large. You know, I think we do that actually pretty well. Like I said, but I think that sometimes we get too kind of caught up in the uncertainties, and we fail to underline the robustness of some of the main results that have been robust for 30 years, which are the ones that really should be pushing us towards a mitigation strategy.
Thanks very much for your talk. I think the U.S. Congress does have a recipe for buried sausage.
Oh dear, oh dear.
My question is a spatial one. So I'm in health and interested in health impacts of climate change related to watersheds. So on a watershed scale, are there models or places on the planet where we would expect these fine-scale downscaling or whatever method you might choose to be better than other places? In other words, can the models work better in different parts of the world? And should we be more wary if we're trying to predict how a watershed is going to respond to climate change in one part of the world versus another?
So yes. So the answer is yes. So we have, particularly for rainfall, right? You know, we have varying levels of skill, right? So there's a lot of skill in the highest latitudes, right? We know that there's greater water vapor convergence. We know that we're going to see more rain on snow events than we did before. I mean, all those kind of, we're going to see a greater amount of rainfall or precipitation in total. But right on the equator as well, you know, we're seeing similar things. But the kind of in the arid zone where water resources are actually the tightest, that's where the models themselves give very divergent results. And if you look at I mean, it's kind of interesting. If you look at things in a zonal mean sense, right? You've got the tropics, and then the subtropics, and then the high. You know, those patterns are very robust, right? Right, but that's you know, I'm averaging over the whole globe. But when you go to, you know, the American Southwest or the Mediterranean or India, right? The robustness of the model results is very not there, right? There's a lot of divergence. Now you can kind of break that down a little bit, like, you know, look at specific processes, and it turns out that specific processes have more robustness than perhaps overall precipitation levels, right? So intensity of precipitation when it rains, that's a more robust change. So precipitation becomes more intense pretty much everywhere on land. That's more robust than the actual patterns of change, right?
Spatial
right. Increases in evaporative loss in arid regions because it's warmer and you have greater evaporation. That's more robust than changes in the rainfall amounts, right? So, for instance, in the American Southwest, we can predict that droughts, the impact of a precipitation drought on water resources is increasing because of the evaporative losses, even though we're not making a very strong claim about changes in rainfall itself or the statistics of rainfall. You can make a statement about the persistence of snowpack in the mountains in the spring, which is not persisting as much as it used to because the snow is melting earlier, and the impacts that has for water resources, despite the fact that you might not be able to exactly or even reasonably make a prediction for changes in the snowfall amount itself. Right. So I mean, you know, yeah.
It's linked to temperature. You're pretty good at
Yes. Yeah. You see the pattern, right? So thermodynamic variables are much more robustly predicted than dynamic variables, and unfortunately, rainfall itself is very much tied to dynamics rather than thermodynamics. Over there.
Thanks. It's really interesting. You talked about modeling the glacier period and then the interglacier period. Mm-hmm. What about the tipping points between those sorts of things? And do we have anything that, are there any model indications of tipping points that might be coming?
Okay, that's a very question. Do I have a model that is capable of a priori modeling the transition from the last glacial maximum to the Holocene? The answer is no, I do not. Right? So to do that, I need to have an accurate and functioning carbon cycle and dynamic ice sheets and proper ocean ice interactions and the ability to do Heinrich events and the ability to do all of those things. That model does not exist. People are working towards it, but it does not exist. So our understanding of exactly why that particular orbital cycle triggered the deglaciation, we're stuck with models that are much less complicated. So that does bring up the question, so how confident are you that there might not be tipping points in the future? You're not very. Nonetheless, a lot of the things that people posit as being important tipping points, I'm underwhelmed. A lot of the thresholds that people are talking about crossing, right, so associated with rainforest to savanna transitions, the overturning stream function in the North Atlantic, which we know has multiple states, there's a few other things. But those people talk about methane and things, but we can take that one offline. But I don't think that one has much credibility. But those are thresholds that we know are in the system, but they don't actually have global impacts, right? They have important local impacts, and there are lots more thresholds that are locally important. Right, there's a very, very clear local threshold in Miami in South Florida for when the aquifers become too saline to drink from. At which point, something is going to tip, right? But it's going to be a human response to a set of circumstances associated with sea level rise. Is it going to be 1 foot? Is it going to be at 2 feet? It's going to be somewhere around there. Right? But again, that's important locally, but globally, nobody cares. People care, but it doesn't really impact anybody else. There are tipping points in the Arctic, right? Places that rely on ice roads to get here and there. Those ice roads, the number of days that they can be used is shrinking on both ends by weeks. Does that have important implications for the economy of these regions and the people that live there? Of course it does. The sea ice that doesn't come into to Barrow it used to be 8 months a year, now it's 2 months a year, right? That's a massive change to the local environment and to the way of life of people there. Again, but it doesn't necessarily have a global tipping point. The thing that bothers me most, though, about discussions about tipping points is this notion that that's what we should be worried about, right? The idea that until there is a tipping point, everything's fine and hunky-dory. But then after a tipping point, oh my God, global disaster, and and then, well, there's nothing worth doing anyway because we're all already effed, right? And I don't think that's not a good way of thinking about what's going on. So as warming is continuing, as climate change is continuing, the number of thresholds that are being crossed are increasing everywhere, right? And those are thresholds associated with pine bark beetles or with ticks or with sea ice, but they're everywhere. They're going to be pushed in more and more and more, to be triggered. And the total amount of damages that you're going to get from that, or the total amount of disturbance that you're going to get from that, whether it's to us or to ecosystems or to, it's just going to increase, and it's going to increase at an increasing rate. Right? There's not going to be a point where, oh yeah, well now we've had enough, stop. It's just going to keep on. It's not. So, when people talk about tipping points, it kind of engenders this kind of decision thinking framework that says we don't need to do anything now, and when something happens, there's no point in doing anything. Whereas the correct decision-making framework, given the realities of what's on the ground, is that there's never going to be a point at which it's not a good idea to reduce emissions, right? So it's a good idea to reduce emissions now, and even in 20 years' time, if we've done nothing, it will still be a good idea to reduce emissions. And even if really bad things happen, it will still be a good idea to reduce emissions, right? Because it doesn't stop. right? You know, the difference between a totally burn-it-all climate and one in which we make a serious effort to mitigate is massive, absolutely massive. And there's never going to be a point where, there's never going to be a tipping point in which, you know, it's not worth doing something. So we have to kind of build in to our minds that today, and in 12 years' time, and in 20 years' time, and in 40 years' time, we are still going to be faced with decisions that make the situation worse or that make the situation better. And one would hope that there is a tipping point and we start making decisions that make the situation better far more often than we're doing right now. So that would be the tipping point that I would be looking for.
Human tipping point to avoid any other possibility.
Yes, yes.
Okay, it's me, I think. I'm over here.
Oh, sorry.
Sorry. So I'm going to ask the somewhat naive social science question.
Oh, well, that's good, because I'm totally naive about social science.
Yeah, well, actually, you seem a lot less naive than you're pretending to be. But I guess because this is, you know, a talk like this can induce a sort of existential anxiety, which is a state in which you probably live a lot. I certainly do. And so I wanted to ask you if there are strategies or institutional changes that you see that give you hope, like on both the simplistic division between adaptive and mitigative kinds of, are there things that you look at in the world and say, that's the right direction to be going right now? I mean, aside from the clear idea of just reducing emissions, but how we do that and the justice with which we do that.
So it depends on the day, really. But I have to say I'm more optimistic in the last 6 months than I have been for a long time. Partly because it seems to me that the level of conversation has reached a tipping point, if you like, where more and more serious people are talking seriously about doing something serious. Right, not just greenwashing, not just, you know, pretending that, you know, recycling your bowls and cans is going to suddenly solve the problem. Now, you know, obviously that gets into the realm of pretty contentious politics, but that's where it needs to be, right? You know, like for us to get anything done that's commensurate with the level of the problem, it's inevitably going to be a contentious political issue. And the fact that we're having contentious political debates about it is, I think, a good sign. You know, I mean, people are trying lots of different things with varying success. I mean, like, so, you know, the BC is not quite a poster child, but is a good example of how you can make some progress, right? Not perfect, but, you know, but you have a carbon tax, right? The carbon tax that is not zero is better than one that is zero, right? And we have, you know, in the US, the Regional Greenhouse Gas Initiative in the Northeast is actually reducing emissions from power plants. You know, the number of new coal power plants in the US is zero, right? Why? Many different reasons, but, you know, people are making progress in doing these things. You know, the success of LED light bulbs compared to CFL or incandescent is a massive improvement in efficiency. That's, you know, like you can see, I mean, cities across the US are basically, like, I mean, like New York stripped out every single streetlight in Manhattan and replaced them with LEDs. And you think, well, that's a massive investment. But no, because it paid for itself in like 6 months. Right, so people are doing that. You know, the price of solar is way down. The price of wind is way down. You know, all of those are good signs. Are they on the level that we need? No. But, you know, a journey of 1,000 steps, 1,000 miles starts with, you know, a single step. So we've done more than a single step. And so those kind of things make me a little bit optimistic. But then, you know, other times I'll wake up and like somebody will have said something very stupid on Twitter, and then I think, oh. But you know what? I'm sorry? On Schmidt, yeah, no. If only it was, yes, yes. So, you know, I mean, you know, I've got I shouldn't do this, but, you know, I've got a young daughter who will be alive, hopefully, in 2100, right? So, you know, you see, you know, these things become very visceral, right? It's not just a theoretical exercise. We were playing around in our models and seeing how much we can make the world burn. These are real impacts for real people that we already know. And so those, but then they're delightful and smart and determined. And then you see something like, Greta Thunberg, and you say, oh, okay, it's a very powerful statement that they're sending to us, you, and other people who are not in the room. So that's positive, right? And it takes that realization before people are really going to move. But people, the willingness is there across a whole swath of different things. Getting it across the line to the point where, it's actually making a serious dent in emissions. The UK is doing well. Germany is eventually going to do well. Sweden, Norway are doing okay. The US, bizarrely enough, is doing okay, mostly because of natural gas and fracking. But and Canada, apart from the whole obsession with pipelines and liquid natural gas, would do okay. But these things will work their way out, I think.
Hi, thank you for your lecture. I was just wondering, from an ethical perspective, if you ever thought, if you ever think it's okay to just show the worst scenario to a policymaker, even if you believe it may benefit the most amount of people, or do you think they should always be the most educated to make those decisions?
So that's kind of premised on a situation that never happens, right? That a policymaker who has the power to change anything very radical just goes to talk to one scientist who has an ethical dilemma about what to tell them, right? That doesn't actually happen. But let's grant you this particular climate trolley problem. Would it be better for people to make the right choices according to my ethical framework, based on full knowledge of what's happening, or based on partial knowledge, right? So the problem with making decisions based on partial knowledge is that those decisions are not robust, right? Because knowledge can always be augmented, right? So if your theory of change was that you had to shave the truth in order to get anything done, and then you hope that policymaker doesn't ever talk to anybody else, that would be a very short-sighted strategy, right? Because why is he coming to talk to you in the first place, right? Who am I? I'm not anybody. I'm just a scientist, right? I'm not an ethicist. I'm not a social scientist. I'm not any of those things. So why do I have any standing in the room to be listened to? Right? What is that based on? Okay, it's based on the weird ideas that people have about science and therefore scientists, which are not always very accurate. So, I can benefit a little bit from that. But the main reason that I'm there is because I would be perceived as being an objective, relatively objective describer of the science. Obviously I'm not pretending to be some kind of objective, godlike person, right? But for that to continue to be true, you can't be partial with the truth, because the only reason you're there is because of your credibility. You lose your credibility and you're not there. At which point they're listening to somebody else who is not credible. So ethically, you are emboldened to give the whole truth and nothing but the truth, right? And I don't really see any way around that, nor would I want to.
It's also critical.
You have to use a mic.
Critical in a post-truth world.
Right.
A few of us hold that line, of getting truth into the truth.
Okay, so that's so. I mean, like, do we live in a post-truth world? You know, there's never been any shortage of people who were willing to convince people of convenient untruths, right? I mean, you go back to Plato and the dialogues, and you can see exactly the same thing here. You know, who wins the debate? You know, the rhetorician, not the doctor. So people have recognized that in human discourse for millennia. Right, so that is not different, but we live in an era where it's increasingly easy to kind of seal yourself off in a bubble of your own tribal myths. I don't know, that's not the right word, but you know, like. And you end up in a situation where people are totally impervious to truth, right? Because because people have either put out so much noise that that nobody can distinguish truth from falsehood, which is mostly what's going on right now, or you've got outright people who are paid to lie and push a particular. Push a particular untruth, but actually that's not how things are working right now. Right now, it's an issue of a pollution of the communication environment. Right, you put in more and more crap, you can't see the clear water, and so you're right. You have to be. We have to be on the lookout for ways to filter that water. So that the clarity of what's actually happening can come through, and there's many different techniques that you can use there. One of the most important is to demonstrate your credibility and your trustworthiness. And it turns out that even though people believe you more when you're very, very confident about your results, but people have more credibility in you as a person when you're totally upfront about all the uncertainties and debates that you're actually having in yourself. And so when it comes to communication, right, demonstrating that you're a human being is actually more important than being, dogmatic about your result. And that's a tricky thing to calibrate, but it can be done. And I think it was it Groucho Marx that said, it's all about sincerity. If you can fake that, you've got it made.
I think that's a good quote to end. So I think we'll continue this conversation tomorrow at the workshop on climate communication advocacy. I understand so tomorrow at 10:30 for those of you who are interested. So let's thank Gavin again.
Thank you very much.